Hello friends, welcome back to True Attractive. In this video, we are going to be demystifying what Fourier series is all about. Firstly, we need to understand some certain thing about Fourier. I will skip the part of Joseph Fourier, who is the founder or the mathematician that has to work this out and discuss what Fourier series is all about. The thing here is that it goes this way. Any arbitrary periodic signal, we're going to be discussing about this main point, the periodic signal, right, or function, right, can be represented or decomposed into a series of sinusoids of harmonically related frequencies. This is kind of like grammar. Okay, let's look at what this simply means. But before then, let's further more. Now, the technique used to represent a periodic signal in terms of their harmonic is called Fourier series representation or expansion. That simply means that any arbitrary periodic signal can be represented or decomposed. You can break it down into a series of sinusoid or sine waves, right? And these sine waves is not just one sine wave. It has several sine waves amalgamated together, right, with some harmonically related frequency. The techniques used to break the signal down, right, is what we call the Fourier series representation or expansion. Let's look at the first point about what are periodic signal, which is kind of the first point here. Periodic signal are signals that repeats. Periodic signal, right, are signals that repeats itself or that repeat themselves over a regular interval. That simply means that whenever we have a signal, right, that repeats itself at regular interval, such a signal is what? Is a periodic signal. Right? Look at this. From 0 to pi to 2 pi, we have one full cycle, right? Now from 2 pi to 4 pi, we have another what? Full cycle. So in essence, we are having a complete cycle, and it is repeating itself both in the positive and the negative side. And let's say we shift the signal. This is x of t, right? Let's say we have a signal x of t, then we shift it by pi. Right? It's kind of saying 0 comes to pi. So the signal is starting here, right? So pi goes to 2 pi, right? Then to the next one. So now 0 goes to 0, right? If let's say we're starting at 0, like we said, we had pi, we move it to pi. Then it's kind of you moving the signal, right? You understand? You shifted the signal. And remember, this minus pi goes to 0 and it forms another one here. So it's kind of, it repeats itself at regular interval. As you can see the way it works. That's a periodic signal. An example is the same wave we just discussed, the one in the red line, right? Now, the second component or the second discussion is harmonics. The basic way that you can understand what harmonics is all about is that you can think of harmonic as a version of the actual signal, right? Which in turn affects the signal or changes its form. For instance, if you have a guitar, right, and you hit the string, you have rung, the rung. So that kind of sound gives different what kind of vibration and some other waves. So when they mix together, they form something complex, which is different from a pure sound wave. You get the point? Now let's look at how harmonics works. You understand? Here is a pure sine wave, right? Here is a pure sine wave, right, which is undistorted, right? A pure sine wave. And distorted sine wave, right? It is pure. There is no harmonics, there is no distortion in it. Now, let's say this sine wave, which is pure, we know it's just ideal. It doesn't exist in real life, right? But if we are speaking, we have, let's say, it results not a signal like this, but kind of a signal like this. Let me see another color of pen. It results in a signal like this. This kind of look like a sine wave, but it isn't a sine wave. But you know what? What Fourier is trying to tell us, or Fourier series is going to do for us, is that we can only deal with a sine wave. Right? We can analyze the sine wave. We know about that very well. But the signal is not a sine wave. What can we do? We have to break this down. Looking at this signal is composed of a sine wave, right? And harmonics of this sine wave. Look at this. The blue one is actually the original signal, right? The blue one is the sine wave. You get the point? And the black one is the harmonics. When you mix these two signals together, then we get this signal that I'm drawing here. I mean, is the concept clear? So which means this signal, this distorted signal that I drew before, I know you are just looking at the signal as kind of, oh, what kind of signal is this? This isn't a sine wave. Yeah, but now you know that this signal is composed of a sine wave, which is the actual signal. This is the actual undistorted sine wave, the original message, plus what are harmonics. The black one is the harmonics. It's kind of a sine wave, but not the original information. It's not that much important. It's kind of deform the signal. It's kind of affect the signal and make it kind of different from the original sine wave. I mean, is the concept clear? If we want to make it very complex, if we keep adding more harmonics to it, right? Let's say, look at this signal here. We add another harmonics to it. We get something like this. The more you keep adding, we end up having a square wave. Look at it very well. Is the concept clear? Harmonics, at the first instant, you need to think of it as a smaller version of an actual signal, which in turn affects the signal or changes its form. Here is an undistorted sine wave. Here is a distorted sine wave. And I showed you that this sine wave, which is distorted, has a component of the original message or the original sine wave inclusion to harmonics. Harmonics are this black one added to the original, which is the blue one, right? So in essence, this blue one is actually the sine wave, the original sine wave. We have the black one, which is the harmonics. When you combine them together, as I do here, you combine this and this, you get this distorted signal. You get. Now, after getting the distorted signal we already know before, if you add another harmonics to it, it turns to like this. The more you keep adding harmonics, you can form a square wave. So now, since we have a little bit of understanding about harmonics and what periodic signal is, let's look at what this actually does. The Fourier series is just telling us, okay, I'll help you. If the signal is complex, I can help you to decompose the signal to what? The original signal and its harmonics. By what? Using what we call Fourier series expansion or representation. Now, here's another concept that we need to look at under Fourier series, right? For the periodic signal, right, to be analyzed with Fourier series, periodic signal to be analyzed with Fourier series, it must satisfy some certain condition, which we call the Dirichlet conditions. I'm going to be discussing about this Dirichlet condition in the next video. It is 3 words. Condition, very simple. I mean, you can memorize them in short. I mean, for example, but actually they are quite simple, right? Those are the 3 conditions. Another point here is that the various techniques used to represent a periodic signal with Fourier series are those 3. But the most important one is 2, which is actually the first one and the second one. The third one isn't that much important, but that much of use case as in academic standard. The first one is actually the trigonometric Fourier series. The trigonometric Fourier series is the one that decomposes it with, if you have a signal, understand, let's say x of t, you can decompose it to have what? A plus b and something plus c and something. So this A is actually the DC value. Then other signals are combined to it. This one will be function of sine. This one will be function of cosine, right? Here's it. X of, we have A, we have B, we have C. This is like the DC value. This kind of a function of sine wave and function of cosine. Because you know a sine and a cosine are almost the same thing, just shifted, right? But the most important I want us to understand here is that we have 3 ways, right? But 2 are the most important. the trigonometric Fourier series, which we'll be discussing in the next video after we discussed about the Dirichlet condition, and then complex exponential Fourier series. I hope the concept about Fourier series is demystified. If there is any question, feel free to let me know in the comment section.